this is concept of the so-called inductive bias, right? The bias assumption you made into the models. You relate to the concept of overfitting and complexity. And again, the examples I give in similar to the previous example is this, right? Suppose I want to learn the observation between y and x here, and then the red dots are the observations here. And then, well, if I assume a linear model and I learn the best parameter, and that seems like a very good fit to this data sets here. And equivalently, I can identify a high order polynomial, seems even a better fit to the observations, right? This is a more complex model than the linear models. Now, however, we care about this interpolation, extrapolation on the unknown test data sets that show up in the green dots here. Suppose I'm going to test the model performance on the green dots. And what do you see for the linear model? Usually what you observe is that the performance, which means the difference between your prediction and your observation. For instance, this will be your predicted value along the y-axis here, and this is your observed value between them. There's a gap between your prediction and your observation, and this is something called an error, and also called a residual. So there's deviation between your prediction and your observations here. But however, you notice this, for the linear model, the deviation, the error between your prediction and your observation is on average, right? Similar between your observations and your new test data sets. And if you pull out the new test data sets here, and then there is a residual, there is difference here. But those difference here on average across all the samples you have here, across all the green dots here, is pretty similar to the error you have on the red dots. So that's what you notice from these observations here. So in essence, what is saying this? So later on, we're going to make it more concrete. What this means that your test performance, the accuracy measurement on the test data set, is pretty similar to the performance, the accuracy performance measured on the training data sets. And that's for the linear model. However, on the other hand, for this type of a high order polynomial models, and that's opposite, and this is not true anymore. If you look at the polynomial functions here, the errors on the training data sets is close to zero because your prediction and overlap almost exactly with the actual observation. They align along these curves at this point here. And however, if you look at the test data set, the green dots here, and then there is a residual between your prediction and your observations here. This is your observation, this is your prediction. The difference between them is this side for this sample, and this is a difference for this training examples here, right? So there's a big difference between them. And now if you look at these dots here, the difference is this. This is your prediction, and this is your observation. The residual is this size here. You can see here, it's much bigger. And then this one is even bigger. This is your observation, this is your prediction. The gap between them is even larger. So what you notice for this polynomial, the model is that the performance on the test data sets is much worse than the performance on the training data sets. So there is this kind of inconsistency between the performance on these two types of data sets. And then, I know, of course, you notice from your previous probably math from other lecture classes, you notice that we call, that this polynomial function, there's an overfitting of this polynomial function on this type of training data sets. And then we say it's too complex for this type of data sets you provided with. So in general, this is a very common observations. So we see that again and again throughout the many machine learning models, and you show this type of behavior. So the behavior is this. Here what I show is the performance, the predictive performance of your model as a functions of the complexity of your model. So right now, I haven't defined how to exactly define the complexity of the models here. But roughly speaking, now for simplicity, you can associate how many parameters, free parameters you have, and for that particular model. For example, on the examples we just have, so the polynomial function and the complexity will be associated with the orders of polynomial. And your seventh order polynomial will be more complex than linear functions. That will be the first order polynomial functions. And the second order will be quadratic functions of that. So you can see the complexity will be correlated with the orders of the polynomial. That will be, being a simple sense for the polynomial functions of that. So what do you typically see is this? On the training data sets here, and suppose you measure the difference between your prediction and your actual observation, and you call that error. On average, the error would decrease as a function of the complexity of your underlying models. The more complex model it is, and the less training error you typically will see. So that's very common for many machine learning models. However, what we are interested in is not performance on the training data, because eventually all the model we learn from the data, we would like to use it in practice. So which means that we want to see the performance of the model on the unknown test data sets. So that's what you usually, what the values of the models, right? So we care more about the performance on the test data sets. And that's usually the behavior you typically will see for many, many machine learning models. Not all, but for many machine learning models, look something like this. So as you increase the complexity of the models, and in your testing performance getting better, right? So error become decreasing as you increase the complexity. But after a certain point here, when you further increase the complexity of your model, your performance is actually getting worse. So error will increase when you further increase the complexity of the model. So you have roughly this type of V-shaped distributions, V-shaped curves on the performance on the test data sets. And then the kind of a monotonic decreasing curve on the performance on the training data set. And this type of thing is very common. So, in addition, what you typically see is that this kind of typically what you see, this kind of green curves is kind of always above these red curves. And that typically say that because you are testing on the test data sets, you expect that the performance is worse than the performance that you see on the training data sets here. So, and which model should you choose, right? You can see now the x-axis contains a collection of all the models you might have, right? So we're going to talk about all these different kinds of models in this class. So in the end, and you have to pick up one, right? Because in practice, you have to give people a model, say, this is my prediction. And which one should you choose? Well, if you have this type of curves, and that give you some guidance for choosing the perfect models, and that would be the ideal range of the models you would like to pick for solving your particular problem. Because on this range of the models here, you have your ideal range of model complexity, and the testing performance achieve roughly the minimal point along this range of that. And overall, we said that within the left side here, and this side here, and your error is high performance is not optimal because your model is underfitting. So which means you have enough data sets, but your model is too simple to fit the data sets here. It doesn't have enough capacity to fit in the data sets. And then we said it's underfitting. On the right-hand side here, and then we say your model is overfitting because your model is too complex to train on the data you have here. Right? You might have 100 data, but the model you have might have thousands of parameters on your models. If you try to learn those thousands of parameters based on 100 observations, you're more likely to overfit your models, right? You can achieve a fantastic training performance, but a very poor testing performance. So this regime is that you're overfitting your models. On this regime, you are underfitting your models. And ideally, if we are lucky enough, we can try all kinds of models. In the end, we're going to pick up the ones sitting in this sweet spot, in this ideal range of complexity, and this is the model you should choose. So of course, I'm plotting these type of curves here, and it's challenging because these curves here is not always look like this. Maybe it's slightly more complicated. And also, in addition, I want you to mention that these curves here depends critically on the data you have and the number of training samples you have. And if you have many training samples you have, right, the number of training samples is very large. You have sufficient amount of training annotated data sets for training. You might be able to push your ideal range of complexity to the right-hand side here. And then in that case, you can afford to use more complex models to train on your data sets. And this is something we're going to notice we're gonna come back on this type of curves and again and again throughout the lectures. But I'm hoping that you can keep this type of curves in mind when you think about different type of machine learning models. All right. And the question is, how do we do? How do we pick the right models here? If we are only provided a set of data sets here, we don't know the real test data. What should we do?